Howdy, partners! Welcome to the second episode of a series where I will be developing an adventure game framework for Unreal Engine, starting with the interaction system. In the previous video, we implemented the detection of interactable actors in range with the player character. However, no selection or filtering was made, and we were left with objects hidden behind a wall and that shouldn't be interactable. I initially wanted to merge this video with the next one, but found out that there was enough substance to treat this topic independently. The goal of this episode is to achieve the result shown here. I know it is very underwhelming, but we will have an updated list of interactables actors where only those that are out of view being filtered out. And this is actually slightly trickier than it looks if we consider some fringe cases I added. Also, when making this video, I realized I previously did a little oopsie out of habit by setting trace complex to true in the multisphere tracing for objects. While it is totally harmless in this context, we will see today why it actually is a pretty good example of a use case where trace complex is useless and should be left to false. So, in this episode, we will address occlusion culling with the implementation of a visibility check that allows the removal of these hidden actors. As you may have noticed, I made some changes to the level by applying some texture here and there, because it was depressing and ugly. So now it's colorful and ugly. Anyway, let's get rid of these sneaky objects that lurk out of sight and open the first-person character blueprint. We are going to create a new function that we will call check actor occlusion from location. It will take for input an actor reference, actor to check, and the vector detection location. The output will simply be a boolean is visible. We will add it, along with the function we did in the previous video, to a category, interaction pipe detection. Since this function will not be doing any alterations to the actor input, we can flag it as a pure function for cleaner graphs. Keep in mind that the output of pure functions is not cached, so the function will be re-evaluated as many times as its results is accessed. Since we may reuse this utility function somewhere else in the code, the first thing to do is a check for validity of the input actor reference, for which we will return false if it's invalid. Now we can do a line trace by channel on the visibility channel with the input detection location vector as the start and the input actor location at the end. We must add the input actor to check to the list of actors to ignore, otherwise the trace will always return true due to self-detection. We set draw debug type to for one frame, for real this time. We take the bool return value, feed it into a not boolean, and return the result. Let's now go back to our detect interactables at location function and call this newly created function with the hit actor pin from the hit structure, and we forward the detection location vector located inside this function's scope. Since the validity check will be performed inside the new function, we can get rid of the isValid node inside this one and simply check for blocking hit and visibility. With the hit actor pin from the hit structure, let's compile and see the result. Great! We got rid of the one that is hidden behind the wall. But wait, we also got rid of this one that is at the bottom of a pile, and of this one that is inserted in the static cube. And also of this one that is definitely visible but located inside an alcove. What in the holy baguette is going on here? Let's start with the alcove. This is where the trace complex parameter will become relevant. I'll open the static mesh to take a look at its collision settings. There are two collision meshes in Unreal Engine. The simple one, which is here simply a box that surrounds the recess, and the complex one that follows the triangles of the static mesh and that includes it. In our case, the simple collision will be used for tracing, which means it will occlude the interactable that is inside it. When we toggle trace complex, tracing will be done using the complex collision mesh.
No shit.
And we will be able to reach our interactable and detect it as visible. In the case of our initial multisphere tracing, it is useless because we don't need a pixel-perfect location of the interactables, only a list. So we have fixed the issue with the alcove, but we now have to address the other two objects that are being called despite being partly visible. The reason is pretty simple. We are checking for the absence of occlusion from the camera to the dead center of the object. So in both cases, the line trace hit either the surrounding static mesh or the other interactables, even though the object is clearly visible. We need to refine the check with more traces that will either target the faces, the vertices, or the edges of the actor bounding box. Targeting the faces should be plenty enough, but for the sake of completeness and because I like to over-engineer things, we will implement these three methods. First, we create an enumeration that we will call interactable visibility check mod and create 4 entries. Origin, which is our current mode, faces, vertices, and edges. Back to our function. We introduce a new parameter check mode of the enumeration type we just created. Mark it as config variable and put it in the interaction settings detection category. This time, we are going to define lists of vectors that correspond to the coordinates to which we will raycast for visibility, for each case we defined in the enumeration. We get a select node where the index will be our check mode parameter. You can see that by default the input and outputs are gray diamonds, which are wildcards that can be of any type. Unfortunately, forcing a type in Unreal required to resort to a hacky trick, where we will drag a make array node. This one will also have wildcard. We pull out a vector 0 and drag its output pin to the input of the make array node, and then the output of the make array node to the input of the select one. Now you can see that we have vector arrays as inputs and outputs. Let's make an input array for each of the 4 modes we have defined. The actor boundary box is defined by an origin coordinate, that is the center of the box, and a vector box extent that contains the half sizes in each direction. I will define normalized coordinates with respect to these half sizes so that they will take only 0, 1 or -1 for values. First case, the origin mode is simply 0, 0, 0, which is the vector 0 we grabbed earlier. So far, so good. On the cube there are 6 faces, whose coordinates are any combination where one axis is either 1 or -1, while the other 2 are set to 0. Vertices coordinates are any combination of 1 and -1 for all 3 axes. That makes them 8. Finally, for the edges, it's combinations of 1 and -1 for 2 axes, while 1 is set to 0. There are 12. That makes a total of
27
vectors entries. Let's fill these arrays.
1 eternity later.
Okay, now that it's done, we can now take the output of the select node and fit it into a for each loop. We grab the actor bounds for our actor to check. and do an element-wise multiplication of the array element with the box extent. I also want to introduce an additional float parameter, occlusion check bound scale, that will allow to tweak tracing to be able to check inside the box, so we can make the visibility requirements more or less constraining. Default value is 1, so we take exactly the box boundaries. We add the actor bounds origin to that vector and feed the result into the end input of the line trace node. Detection location is still the starting point, and we still need to ignore the actor to check. Finally, we get the output boolean of the line trace. Feed it into a branch, and on the false part we return true to is visible. On the other hand, on the completed pin of the for each loop, we return false. What happens here is that for the first trace where there is no collision detected on the visibility channel, which means the actor is identified to be visible, we will break the loop. Otherwise, if the loop reaches its end, it means that we have not found any part of the object that is visible, and it can be called. Let's set the check mode to faces, compile, and we can check the result now. Beautiful! We now properly detect every fringe case displayed here, with the recessed cube, the object that is at the bottom of the pile, and the one in the alcove. Just for illustration purposes, I will make the occlusion check bound scale parameter change continuously on tick as a function of time. I will also add shortcuts input to change the detection mode at runtime. Let's see what can be done with that function. So now we can see that the line traces pulses from the box edges to the inside, as expected, and we lose the visibility for the recessed cube when the scaling factor gets small enough. When switching to the vertices, or the edge mode, we see that more traces are done for the object that is hidden behind the wall. We can also notice that for visible objects, less traces are being made, since once one manages to reach the bounding box without being obstructed, the loop is interrupted and the object flagged as visible. Okay, all is fine and dandy. Checking the face's visibility will be plenty enough for our needs, but I wanted to implement the other modes as well because I want this framework to be as customizable as possible. We now have a clean array of detected interactable objects, pruned of those that are out of view. No selection of the best candidate yet, and this will be the topic of the next video. In the meantime, I invite you to check the demo of Astinia on Steam, the dark fantasy game for which I am providing programming support to solo dev Mentos Lapas, the marble-chiseled Hellenic legend of atrociously cluttered project folders. I have been told that my use of rage comics and memes was completely outdated, but I am old enough to have earned the right to be obsolete. From now on, I will provide a copy-pastable version of the blueprint we are developing on the videos using the fantastic tool available for free on blueprintue.com. You can find them in the description. Anyway, I hope you enjoyed this video. I'm still very inexperienced when it comes to making video tutorials, so if you have any constructive feedback and suggestion to improve, you are more than welcome to tier me a new one in the comment section. Please like, subscribe, blah 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 blah. Bye!